Good day everyone, I'm Lucas Chan. Today I will be presenting on the behavior of light in relation to the human eye. This topic is fundamental in physiological optics because light is the very basics of vision. Without light, our visual system would have nothing to process. In the next few minutes, I'll walk you through how lights behave, how it interacts and the eye structures, and how this relates to vision and common refractive errors. First, let's begin with an introduction. Light is a form of electromagnetic radiation, and only a small portion, which is the visible spectrum from about 400 to 700 nanometers, is useful for human vision. The eye is specially designed to capture, bend, and process this light into images. The aim of this presentation is to explain how light interacts with ocular structures to describe physical phenomena like refraction and reflection, and finally to connect these principles to vision and refractive errors. Light has a dual nature. It behaves as both a wave and a particles. As a wave, it shows phenomena like reflection, refraction, and interference. As photons, light particles trigger chemical reaction in our photoreceptors. When light travels through different media, its speed changes depends on the medium refractive index. For example, light slows down when it passes from air into the cornea, which bends the light rays. The four main behavior of light in the eyes are reflection, refraction, absorption, and transmission. Now, let's follow the journey of the light through the eye. Light first enters the eye through the cornea, then passes through the aqueous humor, the lens, and the vitreous humor before finally reaching the retina. The cornea does most of the focusing, the lens fine-tunes the focus, and the retina acts as the screen where the image is projected. This structure is transparent to allow maximum light transmission, and even small disturbance can affect vision. The cornea is the eye's primary refractive surface, contributing about two-thirds of the total optical powers. Its smooth curvature and high refractive index compared to air cause light to bend significantly as it enters. Interestingly, the cornea stays transparent because its collagen fibers are arranged in a highly regular pattern. If this pattern is disrupted, as in keratoconus or scarring, vision becomes blurred. Cornea shapes irregularities are also a major cause of astigmatism. While the cornea provides most of the focusing powers, the lens is responsible for fine adjustments. It can change its curvature through the action of ciliary muscles, a process known as accommodation. When we look at a distant object, the lens flattens. When we look at near object, the lens becomes rounder, increasing its power. With age, the lens loses elasticity, leading to presbyopia, a common condition where near vision becomes difficult. The aqueous humor is a clear fluid between cornea and lens. It nourishes avascular structures like the cornea and lens, and also help maintain intraocular pressure. The vitreous humor fills the larger posterior chamber and keeps the eye's spherical shape. Both of these media allow lights to pass through with minimal scattering, ensuring that the image remains sharp on the retina. Ultimately, all the bending of light has one goal: to form a clear image on the retina. The cornea and lens works together to converge light rays so that they meet precisely on the retina surface, ideally at the fovea for sharper central vision. The image form is actually real, inverted, and smaller than the objects. Our brain then processes these signals and interprets them as upright and meaningful images. That coordination between optics and neural processing is what makes vision possible. Beyond basic refraction, the eyes also encounter several optical phenomena. First, dispersion, a separation of white light into colors, which is why chromatic aberration can slightly blur image. Second will be aberration. These include spherical aberration, coma, and chromatic aberration, all of which distort image if uncorrected. The third one will be the total internal refraction. This principle is applied in clinical instruments like fundus cameras and fiber optics, which is used in ophthalmology. This phenomenon reminds us that the eye, although remarkable, is not a perfect optical system. Now, let's connect optics to clinical reality. Myopia or nearsightedness occurs when light focuses in front of the retina. Hyperopia or farsightedness happens when light focuses behind the retina. Astigmatism results from irregular curvatures of the cornea or lens, causing light to focus unevenly. Finally, presbyopia develops when age, as the lens loses its ability to accommodate. Understanding these errors is crucial for optometrists, as correcting them with glasses or contact lens is part of everyday practice. To summarize, light behaves in predictable ways. It reflects, refracts, transmits, and can be absorbed. The cornea and lens are the main optical structures that bend light from an image on the retina. Other ocular media like the aqueous and vitreous humors mainly maintain clarity and shapes, while the eye is highly efficient. Imperfection leads to refractive errors and optical aberration. By studying this principle, we can better understand vision and provide effective correction. This is why physiological optics form the backbones of optometry. Finally, here are the references I used in preparing this presentation. They include Bennett and Rabbit's Clinical Visual Optics, Borish Clinical Refraction, and Assistance and Smith Optics of the Human Eye. These sources are fundamental texts in optometry and provide detailed explanation of ocular optics.